Hi, I'm Dipanjan Ghosh, a student at the University of Minnesota, working in Professor Xiang Cheng's lab. This is a recorded version of my APS March meeting talk, where I talk about activity-induced collective behavior in confined bacterial suspensions, and I discuss the experiments that we have done using light-controlled Escherichia coli bacteria. So, as we all know, bacteria are all around us. They can be found in pores of our skin and in the soil near the roots of plants. And from these two examples, it is clear that the natural habitat of bacteria often involve confined environments. Moreover, recent engineering applications have used suspensions of bacteria confined in microfluidic devices to achieve tasks, such as rotating these gears and extracting useful work. So, to both understand how bacteria affect biological processes as well as to use them in future engineering applications, it is important to understand how bacteria move collectively in confined geometries. Now, the collective behavior of bacteria has been well studied in both two dimensions, such as on agar plates, as well as in three-dimensional bulk swimming cases. However, in case of bacterial suspensions in confined in channels where the gap width is comparable to the bacterial cell size, or in quasi-two-dimensional systems, the collective motion of bacteria has been less well studied. And the connection between the collective behavior exhibited in this geometry to those observed in 2 dimensions and 3 dimensions also remains unclear. So to gain a better understanding of the collective motion of bacteria in confined geometries, in our experiments, we confine a suspension of E. coli between a glass slide and a cover slip, and we use a bright field microscope to obtain images of this setup. And our E. coli have been genetically modified such that by changing incident light intensity, which is controlled by changing the voltage across the light source of the bright field lamp, we can change the swimming velocity. Now, as you can see from this plot here, if the voltage across the bright field light source is increased, the swimming velocity of bacteria also shows a corresponding increase. Now, with this experimental setup and this strain of E. coli, we want to ask the question, how does the collective motion of bacteria in confined systems depend on both the cell density as well as the swimming velocity? To get started, we obtain images using a bright field microscope. These raw images are then thresholded and skeletonized. Then by segmenting the skeletonized images, we're able to extract the positions and orientations of individual bacterial cells. To quantify the collective motion, we define some order parameters. First, we have the nematic order parameter, which is cosine twice the difference in angles made by the cell bodies, which is then averaged over all possible pairs in the field of view. We also define a cluster order parameter, which is the same quantity, but the averaging is restricted only to the 12 nearest neighbors of each cell. We also have an orientational correlation function, where we capture the correlation between the orientations of cell bodies of bacteria located at a specific distance, and by capturing the decay of this orientational correlation function, we're able to extract a correlation length, which is the length scale of the collective motion of bacteria. With these tools, let's see what happens when we ramp up the light intensity at time 0 from a low intensity to high intensity. As you can see from this video here, bacteria start off in a disordered state, and as the light intensity is ramped up, they start swimming and gradually form a long-ranged aligned state having nematic order. If you look at the video from the top left of your screen to the bottom right, bacteria are aligned, and we call this state a nematic lane state, as bacteria are swimming both parallel and anti-parallel to this direction. This is also captured in these plots here. At time 0, as the light intensity is ramped up, bacteria start swimming, which is captured by an increase in the swimming velocity. And correspondingly, the nematic order parameter also shows an increase. If we look at the distribution of the cell bodies of bacteria, as time progresses, we see a sharpening or narrowing of this distribution, which also validates the hypothesis that activity or swimming velocity is responsible for bringing about a transition from a disordered state to a long-ranged aligned nematic state in confined bacterial suspensions. We also measured the steady state order parameters for a range of different light intensities or swimming speeds, and as expected, if the light intensity is increased, there is a corresponding increase in the nematic and cluster order parameters. The same trend can be seen for the correlation length, and these results again validate that by increasing the light intensity or the swimming velocity, there is an appearance of a long-range nematic order in the system. Next, we wanted to study what happens if the density of the system is varied. Now, the first video I showed you was at an area fraction of about half. Now, if the density is decreased, we see that even if the light intensity or swimming speed is increased, the order parameter does not show much change. However, if the density of the system is increased, although the nematic order parameter almost stays flat, there is an increase in the cluster order parameter at high light intensities. Now, how can we explain these phenomena? Let's take a look at a case-by-case basis. At low densities, as you can see from this video here, there are not enough collisions or interactions between the bacterial cells, and as a result, even if the light intensity is increased, there is not much change in the order parameters, and the system remains disordered even at high light intensities. If the density of the system is increased, as you also saw from the first video, now there are enough number of collisions to induce ordering in the system, and the bacterial suspension forms a long-range nematic order, again from the top left of your video to the bottom right. There are nematic lanes where bacteria are swimming both parallel and anti-parallel to each other. Now, if the density of the system is further increased, as you can see from this video here, there is the emergence of these local clusters of bacteria which emerge out of the nematic lanes. And finally, it is the chaotic motion of these clusters that lead to a decrease in the global nematic order parameter at high light intensities. However, since the clusters are locally ordered, the cluster order parameter still shows an increase at high light intensities. Finally, to summarize our results, we showed that at low and intermediate values of density, by increasing the swimming speed or light intensity of the system, we can bring about a transition from a disordered state to a long-range ordered aligned nematic state. As you can see from this green curve here, if the light intensity is low, the order parameter of the system is also low, indicative of a disordered state. However, if we increase the light intensity to 18 volts, the increase shown by this black curve here, it corresponds to the appearance of long-range nematic lanes in the system. However, at high densities, the emergence of local clusters in the system brings about a decrease in the global nematic order parameter. This is also summarized in our phase diagram here. As you see for low densities and low light intensities, there is a randomly disordered state. However, at high densities and high light intensities, we see the emergence of swarming clusters. So our key result is that in confined bacterial suspensions, the long-ranged nematic lanes, shown by the red in this phase diagram, is an intermediate step while going from the randomly disordered state to the swarming cluster state all the way up here. So with that, I'd like to formally end my presentation and thank our group members and my supervisor, Professor Xiang Cheng. If you have any questions, please feel free to reach out to me either via Twitter, or my contact information is also available on our research group website. I'd also like to address a question that was asked to me while giving an online version of this presentation, and that is, what is the significance of the number 12 while choosing the nearest name, while defining the cluster order parameter of the system? And the answer is that we tried different numbers of nearest neighbors, as you can see from this legend here, and the cluster order parameter showed the same trend irrespective of the number of nearest neighbors chosen. And currently we're trying to work on defining a new cluster order parameter which is independent of the arbitrarily chosen number of nearest neighbors. So with that, I'd like to end my presentation, and please reach out to me with any questions you have. Thank you.